Okay, there's a question about Gauss's law, and let me clarify one thing that I did wrong at the beginning, and then we'll try to rectify that as we go through. The central part of the argument is completely valid, but I missed a constant because I was just trying to make the connection between the divergence theorem and the and Gauss's law, which is just a version of the divergence theorem. Okay. So the divergence of your electric field is what? Well, the electric field would be an integral of 4 pi kq over r, because that's your basic idea for the electric field. Now you integrate that over all charges and with respect to distance and so forth, so I don't go through the details of that, but that follows that the divergence of E is then going to be 4 pi k times your charge density rho. Okay, and I said here that the density was the divergence of E. It should be the density times 4 pi k. Okay, so there should have been a 4 pi k here. So what we get when we integrate this divergence is 4 pi k times the total charge enclosed in the volume. Now, that's what we get when we integrate the divergence. We're just integrating 4 pi k times the density, so we get 4 pi k times the total charge, integrating the density with respect to volume. Over here, we're integrating the flux of the electric field, and we know that from the divergence theorem, the divergence of any field is equal to the surface integral over of the field of the normal component of the field with respect to surface area over any surface that encloses this volume. So this volume region is enclosed by this surface region, and this is just a statement of the divergence theorem. Now, this integral here is what we call the flux, and that you should be able to relate that easily to the idea of flux, because, of course, we talk about flux in this course. You talked about flux in your multivariable calculus course. Okay, so the question then is, we have a 3 centimeter sphere with a 7 nanocoulomb per square centimeter charge density over the surface. So, well, the surface area is 4 pi r squared. So the charge on the surface is 4 pi r squared times sigma, which is 252 pi nanocoulombs in this case. And the nanocoulomb is part of this expression. Okay, this isn't anything walling something off. It's an arrow from this yellow stuff to this yellow stuff. And there's an error in there. I got the 4 pi k kind of messed up. So we'll correct that when we get to it. But the main thrust of the argument, the main thrust of an application of Gauss's law is that it works well if you can construct a surface enclosing charge, as we're going to do here. We're wanting to find the electric field at a distance of 10 centimeters from the center of this sphere here that contains this charge. Okay? If we can sketch a surface on which the electric field is known by symmetry or by some other means to be uniform in magnitude and also perpendicular to the surface, and that's going to be the case here, then our integral of E dot n ds, since E is perpendicular to the surface, it's parallel to the normal vector, so we just get E with no vector here, and we're integrating that over the surface, and it's constant if we fulfill those conditions, one of which is, again, that E is constant. So we just multiply the electric field by the area of the surface. Now, conveniently, in this case, we're going to see that if we draw a surface, a Gaussian surface, okay, the surface of radius 10 centimeters, centered at the center of our charge-carrying sphere, that the electric field is going to be both uniform on this surface and it's going to be radial. It's going to be parallel to a line from the center out to the point at which we're looking at the field, which means that it's going to be tangent to the sphere and therefore perpendicular to the surface increment and parallel to the normal vector, as is the case, as is required in order to use this to calculate an electric field. Okay, so now I'm not going to go through all the symmetry arguments. By rotational symmetry, we've talked about the symmetry arguments. We're trying to do a summary here, trying to answer some questions. So you can review, you can look it up, you can read it in the book, you can look at the notes when we went over this. But anyhow, by rotational symmetry, it follows that at the surface of a 10-centimeter sphere, the electric field has to be radial. If it wasn't radial at a point, say this point, then when I rotate the surface, it's not going to be radial down at this point. Okay? But, you know, it's going to be something else here. So the rotation will have violated the fact that if I rotate this sphere in here or this sphere out here, or rotate the whole picture, the field shouldn't change, because the field is simply the field created by a charge uniformly distributed over this sphere. So that uniform distribution of the charge over this sphere doesn't change when I rotate things. We can't change the electric field out here. So in the first place, the direction of the electric field turns out then to have to be radial from the center. And radial really kind of gets it. Okay. Also, then it's perpendicular to the surface of the sphere. And also it's got to be of constant magnitude, because again, if we rotate this thing and we find that the electric field at some point was not the same as at other points, but we rotate it, then the point where it's not the same as at other points is down here, not up here, and that violates rotational symmetry. So also by rotational symmetry, the electric field has to be of constant magnitude. That implies that the electric field dotted with the normal vector is just equal to E, which is constant. Now, it could be plus or minus E, because E stands for the negative magnitude of this, but we can regard this as plus or minus if necessary. Not going to address those fine points. I think you should be able to think them through. So that the integral of E dot n ds is just E times the integral of ds over the entire surface, which is E times the area of the surface. Now, we come up here and I'm going to have to make a couple of corrections because I didn't include the 4 pi k in the integral of the divergence, in the integral of the charge density. So it's going to be that E times the area of the surface is 4 pi k q, not just q. So I'm going to make that correction. Okay, it's not pretty, but here we now have the correct equality, 4 pi k q. And yeah, I gave you the principle. This is why the principle works. But I gave you the principle originally, saying that the flux of any enclosed charge through any surface surrounding that, enclosing that charge, is 4 pi k q, where q is the total charge within the surface. And the total charge within this surface is just the charge on this sphere, this 3 centimeter sphere, the 10 centimeter surface surrounding the 3 centimeter sphere, concentric with it. And the charge on the sphere was 252 pi newtons coulombs. Okay, so we have 252 pi, and it's not Newton coulombs, it's nanocoulombs, 252 pi nanocoulombs multiplied by 4 pi k divided by 4 pi times the 10 centimeter squared surface area of this sphere, because the flux is now distributed over the 10 centimeter sphere. We're going to have to divide by the area of that sphere. So this field of equal magnitude and always perpendicular to the surface of the sphere, as we see by the rotational argument, has to be then the total charge enclosed times 4 pi k divided by the surface area. And I just put an etc. up there. It's very easy to complete the calculation. Okay, now just to complete the thing, I'll do the etc. real quickly. The nano here is 10 to the negative ninth. Your K has a 9 times 10 to the ninth in it. So the nano times the K just leaves you 9, okay, with the units of K, which are Newton meters squared per Coulomb squared. Now the 4 pi here could be divided by the 4 pi here, so that goes away. So we just have a factor of 9 here. 252 pi is about 800, a little less than 800, but let's round that off to 800. And then dividing by 10 centimeters quantity squared, that's 1/10 of a meter, so that's going to be 100th of a meter squared. That's going to give us another factor of 100, so we're getting something like 80,000. And then we still got that 9 there. Multiply 80,000 by 9, we get about 720,000. The 8,000 was a little high, so 720,000 is a little high. So I'm going to say this is about 700,000 newtons per coulomb. You can entertain yourself by verifying or invalidating that solution. It's worth the effort to see if you can catch me in an error. Of course, I'm making so many of them that's hardly a challenge anymore. You get 700,000 newtons per coulomb, about 7 times 10 to the 5th newtons per coulomb, which seems about right.